Learned about body-centered cubic, face-centered cubic, and hexagonal close-packed crystals. We learned about these three basic types in detail because they are the most common crystal types for metals, as shown here by this periodic table indicating the crystal structures of the metals. So we looked at simple cubic, and we understood that simple cubic is a very rare crystalline structure in metals. Body-centered cubic is more common. For instance, iron has a body-centered cubic structure, and face-centered cubic is also very common. It's a close-packed structure, so it's sometimes also known as cubic close-packed. We also looked at hexagonal close-packed and how the stacking sequence determines whether a close-packed structure is hexagonal close-packed or face-centered cubic. We're going to look at the characteristics of lattice types, and before we introduce the ideas of lattice parameters. There are 6 possible lattice parameters: the side A, side B and C, and the angles between the edges of the unit cell. The number of lattice parameters is reduced if there is symmetry in the lattice in the unit cell. So for instance, in a cubic cell, all sides are equal and all the angles between the sides are 90 degrees, so only one lattice parameter is required to describe a cubic crystal. Let us look at the important characteristics of crystal structures. In the previous slide, let me just reiterate the importance of A, the lattice parameter. For cubic crystals, we can see that this is the length of the sides of the cube that forms a unit cell. In the hexagonal unit cell, A is the size of the parallelogram that forms the base of the unit cell. If we assume that the crystals are formed out of atoms which can be modeled as hard spheres, which pack together, we can use simple geometry to calculate the relationship between the lattice parameter A0 and the radius of the atom, the atomic radius. This is known as the A0 versus R characteristic. In simple cubic, it is 2R. In body-centered cubic, 4R. It's 4R. A0 equals 4R over root 3. And we will go over the derivations for the cubic systems. Another important characteristic is the number of atoms per unit cell. In a simple cubic, the number of atoms per unit cell is 1, because each corner has 1/8 of a full sphere. Adding up the 8 corners gives us 1 atom per unit cell. With body-centered cubic, we see that we have the corners each with 1/8 and a full sphere at the center. This means that there are 2 atoms per unit cell in the body-centered cubic structure. In the face-centered cubic structure, we see that each side has half an atom, so that contributes 3, and the corners contribute 1. So there's 4 atoms per unit cell in the face-centered cubic structure. And we already discussed in the previous video that the hexagonal close-packed structure has 2 atoms per unit cell. The coordination number is the number of atoms that each atom is in contact with within the crystal structure. In a previous video we explained using a model how in the close-packed crystal structures the coordination is the highest. The coordination number is the highest at 12. And in the previous videos we also saw how the coordination number, I should say coordination number of the body-centered cubic and a simple cubic system is 8 and 6 respectively. The packing factor is the volume of the unit cell occupied by atoms, and we will calculate this. So, first let's have a look at how to determine the relationship between A0 and R. In the simple cubic system it's very easy. We can see that 2 atomic radii constitute the lattice parameter A0. So therefore we can see that A sub 0 is equal to 2R in the case of a simple cubic. In body-centered cubic, we know that the atoms touch from one corner of the cube to the opposite corner. Using Pythagoras, we know that the length of that diagonal is A0 root 3. And A0 root 3 constitutes 1, 2, 3, 4 atomic radii. So we can see now that A0 must equal 4R over root 3. In the face-centered cubic, we can look at one of the faces and we can see that the diagonal across the face, which has a length of A0 root 2, must be equal to 1, 2, 3, 4 atomic radii. So therefore, in the case of face-centered cubic, A0 is equal to 4R over root 2. But once again, R is the radius of the atoms composing the structure. Of course, we're assuming here that we're looking at crystals of elements, so we don't have atoms of different sizes. I'd like to now look at the packing factor. Let's have a look at the simple cubic. We saw that the simple cubic cell contains only one atom. So if the packing factor is equal to the volume occupied by the atoms divided by perhaps I should be more precise here, this is volume occupied by in the unit cell divided by the volume of the unit cell. So that's the packing factor or packing fraction. For the simple cubic, we can see that that is equal to 4 over 3 pi r cubed divided by the volume of the unit cell. If we express that in terms of r, we know it's equal to 2r cubed. So we get 4 pi over 3 times 8, because 2 cubed is 8, and the r cubes cancel top and bottom. So if we do 4 times pi, that gives me the answer 0.523. and that agrees with the table over here. Let's look at the body-centered cubic now. In the body-centered cubic, slightly more open structure. So if we apply the same equation for calculating the packing factor shown here, we get, well, there's 2 atoms now, so there's the total volume is 2 times 3 pi r cubed divided by the volume. So we can use the relationship between A0 and R for body-centered cubic, which is 4r over root 3. That gives us A, and we need to cube that. When we calculate this out, we can get the packing fraction for BCC. The procedure is the same for the other unit cells. We can use this to determine the theoretical density of a material. Density, or the theoretical density, is equal to the mass of the atoms per unit cell let's just say mass in kg divided by the volume of the unit cell in kg. Sorry, not in kg, in meter cubed. Okay, so let's apply that. In this case, we have iron has a BCC structure, an atomic radius of 0.124 nanometers, and an atomic weight of 55.85 grams per mole. So, applying the above equation, we need to find the mass of the atoms per unit cell. Well, there are 2 atoms per unit cell in the BCC structure. The mass of one atom is going to equal the atomic mass, which is 55.85 that's grams per mole. So we'll multiply that by 1 kg over 1,000 grams to get the answer in kg, and then we have to divide that number, because this is for an Avogadro constant number of cells, of atoms, sorry, 6.02 times 10 to the 23 atoms per mole. This quantity on the top will give us the total mass of the unit cell in kilograms. Now we'd like to find out the volume of the unit cell, but we only have the atomic radius. We can use the relationships we derived earlier on over here to calculate the volume of the unit cell. So we know that one side of the cube is equal to 4r over root 3. In this case, the atomic radius was given as sorry, I went too far, 0.124 nanometers. Nanometers is 10 to the minus 9 meters. When we calculate this out, we are going to calculate the theoretical density. Here I've used the symbol rho to represent density. The theoretical density is always higher than the actual density because the measured density of the material, because in real materials there are imperfections in the crystal, there are vacancies, etc., which reduce the density of the material from the maximum value possible. A lot of the theory of crystals were developed before the technology to actually see individual atoms was devised. And here I'd like to show you a scanning tunneling microscope image of the surface of niobium and selenium. And if we look at that, we can see the spheres represent individual atoms. Here we can see that the ideas that we presented are verified by this picture in terms of it clearly shows a closed packing in this structure. Allotropy and polymorphism refer to how materials can exist in different forms. Allotropy is when an element can be found with different structures. For instance, carbon can be found in a diamond structure, graphite structure, or here we've got the C60 molecule, also known as buckyballs, or Buckminster fullerene. For non-elements, this tendency of materials to exist in different structural forms is called polymorphism.